Hello, everyone, and welcome to today's Python lesson. So this week we'll be talking about sorting algorithms. So let's go ahead and get started. So first, let's talk about what is sorting and why this is an important concept in computer science. So when we're talking about sorting, we're usually referring to arranging data in a particular order. So that could be either in ascending order or descending order. And usually this is done with lists. So today we'll show you several different algorithms that can be used for sorting a list in Python. And we'll also be looking at some code examples and writing our own sorting algorithms. The concept of sorting is very fundamental in computer science. And the main purpose is to make searching for data and analyzing data a lot more efficient. And that's also because many algorithms will rely on using sorted data. So does anyone have any questions about what is sorting? Okay, I guess not. So one such algorithm that would rely on a sorted list would be a binary search algorithm. So that would only be possible if our list was sorted beforehand, since we are essentially um, we're essentially like partitioning our list into two halves every single time. So when we're talking about like the types of data that we could sort, this could really be anything. So most commonly it could be numerical, such as sorting a list of people's heights or sorting your age, or perhaps even like your teachers sorting the grades of every student in the class, although usually that's not done in this country. So yeah, those are some examples, but it could also be with strings, such as either sorting like a roster of students alphabetically by first name or last name. So those are some basic examples of sorting. So now we'll be looking at Python's built-in sorting functions. So there's two different ones that we can use, and then we'll try to create our own algorithms based on some popular well-known sorting algorithms. So the built-in Python functions, they're the sorted function and the list.sort function. So they essentially do the same thing, but one of them will return a new sorted list, while the other one will sort your input list in place. Okay, so now let's do a quick demo for this. Okay, so let's start with a list of numbers. Let's just create a list, and then you can put any numbers in here you want. Okay, so let me add a comment here. So let's try to use the first built-in function, which is just sorted. And remember, this one will return a new list. So let's say sorted numbers equals sorted. So we're calling this function, and then we're passing in the list. So just a note, this will do the sorting in place. So now let's see this in action. Let's first print out the original numbers. And followed by that, we'll print out the sorted numbers. Let me see if I can turn the AI thing off. Okay. So let's go ahead and print this out. And then you can see before we had 529156, and then now we have 125569. So they are indeed in increasing order. Okay, so that was an example of sorting numbers. Now let's try to do a list of strings. So what's an example of a list of strings that one might encounter? So let's say we have a list of different fruits. So let's say we have bananas, apples. So you can put whatever you want here. Cherries, and let's say we have a mango as well. Let's use the other sorting function that will sort in place. So what that means is the function will modify your input list directly instead of giving back a new copy that is sorted. In order to use this function, we will do fruits.sort. Once again, we'll print out what it would look like after we sort it. Okay, so you'll see banana and apple got switched because A comes before B. Does anyone need more time to write this down? Okay, if not, then we'll move on to sorting in descending order. Let's go back to the example with the numbers that we had up here, but except we'll do it in descending order. So let's create a new list, sorted numbers, DESC for descending. And then we'll pass in the original array, original list we created up here. The only difference to make it descending is we can set the reverse parameter to true. Now this will tell Python that we want it to be in reverse order. And let's print that out. Okay, so we're printing out the descending list. And you'll see that indeed it is going to be basically this one, but backwards. So 965521. Okay, so now let's explore some more special types of sorting that you may want to do, and we'll start with strings. So let's say instead of sorting alphabetically, we want to sort the strings by their length. So we want strings that are words that are shorter to be more in the front and longer words in the back. So we're sorting by string length. And we'll go ahead and use the same fruits list that we created. We'll say sorted fruits equals, so this time we'll use the sorted function instead of the in place one. Sorted fruits equals, and then here we'll put the fruits here. Now we'll also add an additional parameter to specify that we are sorting by length instead of alphabetically. So that it would be key equals len. Oh, it's not words, it's fruits. Okay, sorted fruits. And okay, I'm just making sure this is correct. Yeah, 5 letters, 6 letters, 6 letters. Now I'm not sure if we have a tie for the same amount of letters, which one will go first, but just looking at this, I think it's alphabetically, like apple and mango both have 5 letters, but apple comes before. I'm not sure about that, but that's not super important for our learning purposes right now. Now I'll go over some other situations we might encounter. Like, for example, if we want to disregard the case, so like uppercase or lowercase, so we'll sort it case insensitive, which means we don't want to pay attention to the case. So let's create a new list called names. And then let's say we have Alice, Bob, Charlie, and Dave. So I'm mixing up the cases. So we have 2 lowercase and 2 uppercase. Now, if you simply sort it like this, how we did earlier, and print that out, this would be considered case sensitive. So the case will matter here. And what that looks like is even though A comes before B, Bob will still come before Alice because uppercase letters come before lowercase letters. Does anyone have any questions on this? Okay, if not, then we'll see what happens if we sort it case insensitive. How we would do that is sorted names equals sorted names, and this time we'll do key equals str dot lower. So we're telling it we want everything to be lowercase, would be treated as lowercase letters. I'm gonna copy and paste this. And this time, Alice, Bob, Charlie, Dave. Okay, now let's move on to talking about kind of a separate topic, but we'll use it for some more advanced sorting, such as sorting tuples. But we'll have to first introduce what lambda functions are in Python. Okay, so what is a lambda function? A lambda function is essentially a small anonymous function in Python that's defined using the lambda keyword. So previously we talked about regular functions. We would use those, we'd create those by using the define keyword. But a lambda function is anonymous, which means it's unnamed. So we actually don't use define anymore. It can have any number of arguments, but it's very simple. It can only have one expression. Now, you might be wondering when we should use a lambda function instead of a regular function. So this is most often used for very short, simple operations where a full function definition would be unnecessary. Let's go over a simple example to demonstrate the lambda function. So first I want you to, let's first write a simple regular function. This is kind of some basic Python review, but go ahead and take a moment to write a function that would take in a number and then square that number. So return that number squared. So for example, if we passed in 2, your function should return 4. So go ahead and take a moment to do that. And once you're done, you can feel free to copy your function into the chat. This should be really simple, and you should be able to do it in like 30 seconds. Okay, so that should be enough time. So some of you actually went above and beyond and you actually used the input function to actually get a number from the user and then call that function. But we're just going to focus on just creating the function itself. So I'm going to call it square since we're going to be squaring the function. the number. So all we have to do is return x, and remember this means to the power of 2. So that is a very simple regular function to square a number. So as you can see, this function really is only 2 lines of code, and it's something that's very, very simple. So let's introduce an equivalent lambda function instead. So how we would do this is we will say square equals lambda x. So this x is the same thing as this. It's our input, followed by x by a colon, and then x to the power of 2. So that's it. It's just same thing, but in one line. And to call this, we will just print square of 5. And we can also do that here to show that both of them are the same. So we should get 25 both times. Okay, so as I was saying earlier, we were going to use the lambda function for sorting a tuple. Let's say we have a list of students followed by a list of tuples that contain the student's name followed by their grade in the class, let's say. So Alice has a 90%, Bob has an 85, and let's say Charlie has a 95. And we want to sort this tuple by the grade. So whoever has the higher grade should come first. What we're doing here is we're sorting by the second element. In this case, it's the grade using a lambda function. This would look like this. So sorted numbers equals sorted. We're sorting the students list. And for the key, we're going to put a lambda function in here. Lambda. So we're taking in a student tuple as the input, and we are returning the second element. So does anyone remember how to access the second element in a tuple? If not, it's fine. So it's just student sub 1. So index 1 is the second element. Let's print out our sorted list. Okay, I think it should be students. So this was in increasing order. So Bob is actually first. Now we can also make this in increasing order by setting reverse equals true, like we did earlier. So now Charlie is first because he has the highest grade. Let's quickly review lambda functions again. So we want to use these when we are dealing with short one-time operations, such as the sorting keys that we were using here. And these functions are only needed for a very short duration, so we're not reusing them over and over again. So there's no need to define our function. When should we use a regular function instead of a lambda function? So we should avoid lambda functions when we have complex logic. In those situations, you would want to use define for readability and also reusability, because lambdas are anonymous, which means they're kind of harder to debug. And also complex expressions and multi-line operations won't work with lambda, since that only allows us to have one expression. Any questions on lambda functions? Now let's move on to sorting algorithms. So the first one we'll cover today is bubble sort. This is one of the most simple sorting algorithms, and it's relatively straightforward to understand. Bubble sort is a sorting algorithm that works by that repeatedly steps through a list, and it will compare adjacent elements and swap them if they are in the wrong order. And this will repeat until the entire list is sorted. I'll try to find an animation for this so that it's easier to visualize. I'm pretty sure Wikipedia might have an animation. Okay, so let's go ahead and play this animation and try to see what's happening. So it's taking every two adjacent elements, and if they're not in the right order, they will swap. So every time it's going to the next two elements. We just finished the first pass through the list, and we'll keep repeating since we're not done sorting yet. And you'll see that 8 is boxed because 8 is in its final location. So we just finished the second pass, and you'll see 7 is in its final location. So every single pass, we will bring the next highest number to its final sorted location. Now 6 is sorted. And this process will continue until all of our elements are sorted into place. Okay, so now everything is in order. Does anyone have any questions on how the algorithm works before we try to code it ourselves? Okay, if not, then let's talk about the code. Well, let's create a new function called bubble sort, and we're going to pass in an array. So we are going to use the regular way of writing a function since this is obviously way too complex for a lambda function. Okay, we'll need to come up with the logic for the loops, for the for loops that we are going to need for implementing this sorting algorithm. So it's quite easy to see what the inner loop should be doing. The inner loop will be incrementing by 1 every time, and it will compare those two adjacent elements. And if a swap is needed, our program will perform the swap, and then it will move on to the next two adjacent elements. So the inner loop is the number of times that we need to compare and swap. The outer loop will be the number of passes that we need. So when we talk about pass, it's how many times do we have to go through the entire array from start to finish. And from the animation, you'll realize one pass is definitely not enough. Our our list will not be sorted after one pass in most cases. And also, the maximum number of passes we'll need is the length of the list. Because earlier I said every single pass, we are guaranteed to bring the next highest element into its proper position. And since there's only n total elements, if n is the length of the list, then at most n passes will be needed. Okay, so that means for I in range, the outer loop should be the length of the array. That's the number of passes we'll need. So n passes. And the inner loop, this is going to be comparing every two adjacent elements. So it's kind of up to you if you want to start from index 1 or 0, since you can either compare j and j plus 1, or you can do j or j minus 1. So in this case, I'll do j and j minus 1. So we'll start from 1, and we don't need to go up to the length of the array, because like we saw, after every pass, the all the numbers at the end will already be in place. So we can actually stop early. So we can stop at, at length of the array minus I. So that means in our third pass, we know the last three will be, after the third pass, the last three items will already be sorted. So we don't need to compare those items any longer. So we can just stop at the length minus 3. Does that make sense? Now, of course, it wouldn't make your program broken if you did length of array without minusing it, but this will make our code more optimized and efficient since we're not making unnecessary comparisons on items that are already sorted. And of course, it's possible that we'll finish sorting before the end passes at most that it will be needed. So in some cases, we can actually break earlier, but let's talk about that logic after we finish the comparing and the swapping, because that's kind of the main logic of bubble sort. So since we're setting it up from from 1 to the length minus I, we should compare the jth element and the element before that, so j minus 1. So if the element at index j is less than the one before it, then that's a problem because it should be great. Any element should be greater than the one before it. That's the goal of the sorting. So for this, we're assuming we want to sort in increasing order. If this is the case, we'll need to swap those two items. Let me see if I can annotate to make this more clear. So let's say we have 3, and then we had 5. So right now this shouldn't be correct. We need to swap them since 3 should come before 5. So this would be j, and this would be the item at index j minus 1. So if the item at j is less than the item at j minus 1, and in this case it is, we need to swap them. So this is what the code is telling us here. So we need to swap. In Python, we can swap them without using a temp variable, which you would do, which you would need in some other languages. But Python makes it easy for us, and we can simply say this. So this means this will now take on the value of this, and this will now take on the value of this. So we can swap them in one line. And we are done. So we can return the array now. But before that, we can actually make one more optimization, which is in the case that not all end passes are needed, like if it's already sorted before then we can actually break out of the loop early. So we don't actually have to check if it's sorted by looping through the whole list after each pass. Instead, we can add that logic as we are swapping. So after the outer loop, before we begin to scan through the list, we can create a flag called is sorted, and we'll set that to true initially. So we're going to assume that it's already sorted and we don't need to make any comparisons. But if we don't have to, sorry, we don't have to make any swaps. But if we do make a swap, then it no longer becomes sorted. It's going to not be sorted any longer. So we'll set that to false. So after this loop, make sure your indentation is correct. If it's already sorted, there's no point to continue on with the passes after that. So right here we can break. Now what this is saying is that if a if a swap was made, it's not sorted from start to finish. If we don't make any swaps, that means the list was sorted already. Does that make sense? Okay. Now let's test this out. So let's create a new list. 1 3 5 7 9 2 4 6 8 0. And let's sort it. We see that it is indeed sorted in order. So our algorithm works. You'll see that without the is sorted Boolean here, when we have it, we can actually, okay, so if we don't have this Boolean, the algorithm will always make n passes through the array, right? But with this Boolean, we can stop early if the array becomes sorted before all the passes are complete. This optimization would be most important for data that is already nearly sorted. So if it's nearly sorted, we don't need to go through all n passes. And also in smaller data sets, this will be efficient because we can likely stop the program earlier. We'll also look at the performance of this algorithm. So what that means is like, as the length, we'll see how long the algorithm takes to run as we increase the length of our input. So you don't have to do this, but I'm going to import time, and just to measure the amount of time this algorithm will take to run. And then instead of returning this array, which kind of isn't needed since we're sorting in place, let's return the length of the array followed by the time it took to run it so that we can run some experiments and see how our performance will fare. And okay, so this code that I'm about to run, you also don't need to copy it down, but I'm basically going to generate a bunch of test data sets randomly and evaluate their performance. Okay, let's see. Okay, so it took some time to sort all our test sets. Okay, so we generated, you don't have to understand how this code works, but we generated a plot that shows on the x-axis, we have the size of the list, and on the y-axis, we have the time it took to finish sorting in seconds. So what do you notice about how the time increases as our input size increases? You'll see that this line isn't linear. So yeah, the time kind of is growing exponentially. So very, very nice. Some key observations here is that small arrays, like between up to size 1000, they'll sort very quickly. But once we have medium-sized arrays from like around 1000 to 2000, we will see a noticeable slowdown in our runtime. And for large arrays over 3000, they will take significantly longer to run. Let's also examine the best case, average case, and worst case scenarios for this algorithm. And also, you don't have to copy down this code. But what I mean by best case, average case, and worst case is that for like a best case scenario, we have a list that is already sorted, but we're still going to call the sort function and see how long it would take. A worst case list would be it's completely in reverse order. And an average case is just a random list that we generate. And when we run this, you'll see that for a best case, which already sorted list of size 1000, these are all size 1000, it only took 0.000096 seconds. So that's very, very fast. But for a worst case scenario, which is our list was completely reversed to begin with, it took 0.1 seconds, which is significantly slower. And a random or average case, it took 0.08 seconds, so not much faster than our worst case scenario. We can generalize these observations with something called big O notation. So, let's talk about that. So big O notation describes how an algorithm's runtime or memory usage will grow relative to the input size. And in this case, we're going to be examining time complexity. So that translates to like if the input grows by 10 times, how much slower will the code run? And big O always measures the worst case performance. So we're talking about the upper bound. Another thing is that it ignores constants. So when we say an algorithm is big O of 2n, that's the same thing as big O of n. And it only focuses on the dominant terms. So when we have big O of n squared plus n, that simplifies down to O n squared. Some common time complexities you will see are O1, O log n, On, O n log n, O n squared, O2 to the n, and O n factorial. And here I have some examples of some algorithms for each of these time complexities. So an example of O1 or constant time is an array lookup. So when we're looking up like what's the item at the 0th index, this operation is O1. So even if our array is size 1000, we still only have to do one operation here. And I mentioned binary search earlier. That's an O log n operation. And for example, looping through an array is On, since no matter what the size of the array is, we're going to have to make that many operations to go through the whole thing. So yeah, these are some of the common ones you'll see. And bubble sort happens to be O n squared. Does anyone have any questions on this concept? Okay, if not, then I'll show you another visual for time complexity. So on the x-axis, we have the size of our input, and then on the y-axis we have some kind of time. So for a time complexity of O1, you'll see that the graph is basically a flat line at y equals 0 almost. And this is because no matter how big our input is, it's always going to be constant time. Whereas if we had like O n squared, for example, like for bubble sort, we will see this in exponentially increasing this quadratic graph that we saw earlier with this. And then 2 to the n is even worse since it's even more increasing even more fast. Yeah, so the x and y axes aren't to scale. So this green one is actually ON, and it's not to scale because otherwise the O 2 to N and O N squared, they would shoot off the screen too quickly. Okay, so that will be the end of our class today. I hope you all learned a lot about sorting and big O notation. And we'll see you next week. And let me know if you have any questions. Thank you.